Okay, so the recording is now on. I hope everybody hears me both in person and online. And you also are everybody is supposed to see my screen, which right now shows this beautiful LVT logo and nothing else. Okay, so before we start, let me ask you one question I'm really curious about. So the other week I was on a conference, Finnish Mechanics Days, and there was quite a lot of discussions during roundtables about education. So since it's mechanical conference and mechanics, so it applies to mechanical engineering. And people say that like many universities notice that people don't, young people are not very attracted to doing PhDs, and they instead see much more benefits in going to work to industry. So you are not at PhD stage yet, at least. So I was curious. Do you guys think it's something that is attractive to you to do a PhD in mechanical engineering, regardless of it's here or at another university in general? Not really. Yeah. So you think that master's education is kind of enough to get a good job? And well, yeah, I don't think you're wrong in that aspect. So of course it's enough. Okay, interesting. Any opinion from online participants?
Yeah, maybe the PhD can be useful if you want to, I don't know, if you want to stay into the academic environment, maybe be a professor or a researcher.
Yeah, it kind of draws the line currently in Finland, at least. As I see it in a similar way, and I've been discussing with my colleagues. Yeah, it looks like in Finland, mostly people who are attracted to academic career track, they are going for a PhD.
One exception. I've seen like at some companies, they do PhDs at the company to specialize in a very specific field, but otherwise there's not much need. Basically, if you have some very specific thing you want to do at a company, you can basically ask them, I want to do a PhD. When basically in collaboration with the company, do that to also basically have a future promotion coming up in that field as well. But otherwise, it's like.
Yeah, well, I know one recent example. A good guy from our lab, he did PhD and graduated, and then he went immediately for a good job in industry. But of course, I cannot know how would it have been if he did not have this PhD. Would it be the same or not? Yeah, it's impossible to say. Okay, just interesting to listen your opinion. Thank you. Let's go into our things. So today, as I announced last time, we are going to talk about the finite element method, which is pretty much the mostly used in engineering nowadays, in continuum mechanics domain. Like it's dominating. And we discussed previous time that very, very wide range of different problems of different physics can be solved using the finite element methods. Not any problem in the world, but quite a lot of them. So it's important that you have this tool in your arsenal. Of course, if you are going to work in industry, as most of you do, as I see in mechanical engineering. But also, I think that it's quite important to understand how it works. And this is exactly what we are going to do today. So we will try to understand maybe a little bit better, if close maybe some gaps, if there were some, about the very, very nature of the finite element method. So to establish some kind of solid basis, and then you will build on it on your own different tools, different types of problems, different software, and so on. So this is not for today class those things, but the essence of the method is. And before that, as previous time, let me start with a short quiz about, where is my quiz? Here it is. About what idea you have about the finite. Maybe I move this thing so the QR code works from. About the finite element method. It's anonymous again, so no effect on anything, no judgment, just fun discussion, and I try to make questions also to give you some fun today. Okay, so this is the first question. So I put here several things that sometimes at least people believe is the finite element method. And you might be attracted to several of those descriptions. Like, it's not an exact definition, but try to choose the most accurate one. So the one that you believe is the most accurate, and we'll discuss it in a second.
Just
can
a question.
Show the QR code again. I couldn't get it.
Sorry?
The QR code.
Okay, I can show it again. Yeah, it's here.
Thanks. Thank you.
Okay, yeah, also you can use menti.com website, and this number, it's on, well, yes, sorry, yes, I thought I put it here on the top of this slide, but I didn't. Okay, if anybody still misses it, let me know. I will skip back.
I added in on the chat.
Okay. Yeah, maybe I'll spend 30 seconds more on this slide, and yeah, and then we go into questions. Okay, by the way, I see that the number of online participants has increased a little bit, which is good to see. Okay, so we have some answers. Okay. Okay. So let's wait a little bit more, because I can see that just 7 people voted out of, I think we have 13 participants combined online and in class. Okay, somebody else. Well, I intentionally made it so that you see the results, but yeah, to test you a little bit how you want to follow the others, or you want to be something else. Okay, so yeah, I can see that quite a few people, most of people have casted their vote. So let's discuss. So the majority of responses received this methods of splitting a body into multiple segments, which are called elements. And I cannot say that it's completely wrong. Okay, I will show you the right response, in my opinion. But please take it easy, because I don't imply that it's completely wrong. That's what I have started to say, that it is included in the finite element method. So it's a part of the method, but I would not call it the most accurate description, because it's not about geometry, how to split a body. It's just one part of this method, and I would say it's pretty much preliminary part, so how you prepare. But what the method does itself, it allows you to solve some problems. So just by splitting a body into segments, you don't really solve any problems. But what you do solve when you want to find a solution for a problem, you are dealing with partial differential equations, right? As we discussed during previous class. So a lot of things in continuum mechanics can be described using the partial differential equations. like a lot of them. And this is one of the methods, the most commonly used methods for solving those problems. I will later show that it's not, we don't solve them directly usually in finite element method, partial differential equation, but that's a little bit later. So other visualization, yes, it's also used always, like you want to see what is your mesh, what is your discretization, and then you want to see the results, some post-processing things. So yeah, I would say that actually all of the answers are relevant. So they all represent aspects of the finite element method, how you approach the problem. But this one is kind of it captures the essence of the methods the best, in my opinion. So first of all, it's a method for solving numerically those problems. Okay, there are not much questions, just a couple of more. So this is a little bit more, I don't know if tricky, maybe the previous one was tricky enough, but this is a little bit in depth about to dig into your existing knowledge of finite element methods, because many of you, I suppose, have heard about methods and have used it already. Very possible. And so this is just to test if you, how deep is your knowledge? And it's okay if you don't know what are shape functions. For this class, it's completely okay. You are not required to know that. I will explain that today. This is just to test, for me to understand the starting point. Okay, so I see that people are hesitating, but voices are coming. Okay. So functions for interpolating a known value, functions for defining the form factor, and the last two questions, they don't get any voices so far. Okay, I will wait a little bit more for those who want to test before I show the right response. Okay, I'll assume that we can proceed. So I did not trick you much in this question. So most of the answers came to the correct. So this is exactly what it is. This is the nature of the finite element methods. Is we are solving some continuous problems, and for that we are assuming something. We are making some assumptions, and those assumptions are about how our unknown function, whether it's displacement or temperature or electric potential or whatever, how it behaves within each finite element, each of those segments. And that is described using shape functions. I will show that later in more details, but good that you already know that. The answer about form factor, it has to do with shape functions. Of course, they are affected by this form factor. So tetrahedral element will have different shape functions than hexahedral element, for instance, or plane element. Yes, they will be different. So they are connected. Again, it's not completely wrong. I intentionally put in this way, though, so that it's a little bit confusing, but the first answer is the most correct one. And I believe this is, well, not the last, is one before the last. So another thing that you often hear about finite element methods is a stiffness matrix. So that applies to problems where you solve for stresses or strains in deformable bodies. So some kind of mechanical problems in the sense of that you are looking into deformations. So again, you are not supposed to know that necessarily, but if you do, I would be happy to see that. So please don't spend too much time. If you don't know, that's okay. If you know, put your vote, or if you think you know, again, no responsibilities for wrong answers here. I won't even know who voted in which way. Okay. Yeah, that's a little bit surprising for me. Okay, pretty much everybody voted, so I will show the right answer. So it's typically symmetric. Yeah, most of you figured out that it's a square matrix. Yeah, okay, at least for typical problems. And I put some in the description that it's two-dimensional and it's elastic analysis. So no multi-physics involved, nothing like that. And for this case, it's symmetric. So we will see that quite soon. And this is kind of a thing that affects numerical performance quite a lot. If you do a more complicated problem, not just two-dimensional elasticity, but something with coupled fields, for instance, then it usually ceases being symmetric, and that affects the numerical performance. So for the same amount of degrees of freedom, you spend much more time on finding solution. So it's something that people used in computational in science. People take advantage of this symmetry quite heavily, and a lot of methods for faster solving those algebraic equations are based on the assumption that that this matrix is symmetric. So it's good that some of you know that. Otherwise, we will discuss later. Well, this is, I believe, is the last question in the quiz. So a little bit about application of the finite element method. So some of you have already used it. And as with boundary value problems, so you need to specify boundary conditions. But technically, in finite element software, you are not obliged to do that. You can just leave some parts of a boundary without any boundary conditions specified explicitly. Okay? And what does that mean mathematically? So I think this is the most difficult question, I think, in today's quiz. And I put here some words describing what kind of problem it is, because what happens at the boundary naturally depends on the problem that you are solving. If it's a heat conduction problem, there will be one thing. If it's electromagnetic, it will be another thing, maybe different things. And if it's elasticity, it will be third. And I put here some more details. I'm not sure if they help you or are confusing you. They are supposed to serve both purposes. The words that I put, that it's linear isoparametric hexahedral elements. Oh, sorry. Yeah, this is a. Yeah, I started to talk about the next question. Yeah, I'm probably confusing you, but hope you are reading. Yeah, so this is about assumption, how stresses behave. Then the next question. So this is not the last. I thought it's the last. I forgot about this one. So the next will be about boundary condition, but this is about stresses. Okay. It applies within the element. So we have somebody and we have split it into finite elements. So, and then we impose some assumptions with this finite element, which depend on what kind of elements we are using. So, and the question is for those elements that are described here, like how is it assumed that stresses will behave within the element? So can they do something like that or not? Or can they be linear only? Or do they have to be constant at all? Like the assumption. Yeah, this is a tricky question. Yeah, actually, I have two tricky questions. So let me show you the answer. Somebody made it right. So, well, to put it very simply, so the key word here is linear elements. linear implies linear interpolation. Like something is supposed to change linearly within each element. And this something, what is it, is described here, element displacement-based finite element method. So that means that we are solving our equations for displacements. And displacements are our unknown function. And this linear applies to it. So we have linear elements in displacement-based method, means that we assume that within each element, displacements vary linearly. So in one dimensions, our elements, and within each element, our displacements can vary only linearly. And other words are just here to confuse you mostly. Hexahedral is about shape, form factor. Isoperimetric is about how interpolation of the unknown function relates to interpolation of the geometry. Isoperimetric means that we are using exactly the same interpolation. Okay, but yeah, it's I like it that some people chose the last answer, that elements cannot be simultaneously all these things, and I like it because people sense that I put some extra words here that they are not necessary there. No, unfortunately, they can be both. All those things simultaneously. There is no contradiction, but half of those words are really here just to confuse you. Okay, and this is the question that I started to describe you on previous slide, and yeah, I promise you this is the last one. Let's try to do it quickly. So what happens if we don't prescribe any boundary conditions at some part of the boundary? What does it mean mathematically for our problem that we are solving? What will happen there on this boundary? Does it imply something, or so there? I put here quite a lot of different possible responses, and yeah, starting from the most relaxed one, which is already getting that. Means there are no restrictions at all whatsoever on both displacements and stresses. And different versions about that something must be zero still. Okay, 5 people voted. Yeah, I think it's okay. If you don't know and you don't want to put arbitrary vote, it's okay not to vote. So, but it's interesting to see what your opinion, if you do have them. Okay, so very well. Well, I think actually it is. I think it is maybe a bit better than last time when I showed it in a different class, this question. So let me show you the correct answer. This one, and it did collect at least 2 voted, which is good to hear. So this is one takeaway that I want you to have from this slide, from this question, that if you are not imposing anything in your finite element solution, like for instance, you are using some software for that and you are not saying anything about the boundary, it still does involve some restrictions on the solution. And what are those restrictions depends on such thing that is called natural boundary conditions. And natural boundary conditions is something that is included into the variational form. And that is what we are going to talk a little bit. So if you are solving just partial differential equations on paper analytically, if you don't say anything, you don't say anything. But you cannot solve partial differential equations without providing the necessary amount of boundary conditions, right? Because there are derivatives here. You cannot solve with unless you have enough boundary conditions. But when you are using variational approach or weak formulation, you can technically not do that, but that means that still some boundary conditions will be derived automatically from this variational statement, from the variational principle. And those are the natural boundary conditions. We are going to talk about them more today. And yeah, so this is just, I want you to be aware of that it still means that there is something and you need to be aware what it is. In case of three-dimensional displacement-based elasticity, using at least conventional variational principles. Of course, you can do something else, but conventionally, it implies that the stress vector will be equal to 0. Stress vector is a dot product of the stress tensor, Cauchy stress tensor, and normal vector to this surface. So which implies that some components of the stress tensor will be equal to 0. To give some, it's a little bit vague, of course, some components, I know that, but to give more information here, we need to introduce some directions. We need to refer to the orientation of this boundary or refer to some reference frame or something. So yeah, but mathematically in three-dimensional analysis, you can say that 3 components of the stress tensor will be equal to 0. Okay, so there are some this is some restriction. So by not putting any boundary condition, you are saying that there is a 0 force acting there. And 0 force means that stresses at this boundary cannot be absolutely arbitrary. They must fulfill this requirement that they result in 0 force acting on this boundary. Okay, thank you for participating. Let's go into our lecture now. Where is it? It's here. Okay, so outline, I think we already mentioned it previous time, so I won't stay for long on this slide. Again, same books that you can refer to, and yeah, from the great variety of books about finite element methods, this book by Bata is the most close to what I'm going to show you. This is why I put exactly it here. Okay, and we will start with discussing what we just mentioned about strong and weak formulations. When you are reading literature about finite element methods and even documentation to finite element software, you can quite often see these expressions about variational form, variational principle, or weak form of equations. So why do you think we use them at all? Do you think is there any reason? So a bit of maybe not really a spoiler, but what I'm going to tell you, that in the majority of cases, what you do with finite element method in finite element software is you are solving equations, governing equations in this weak form, formulated in terms of variational principles with variations. Do you have any thoughts about why would we do that? We have those very nice partial differential equations that we discussed previous time. Why would we need something else? Okay, it's kind of good that you don't know, because yeah, this is what I will try to explain today. So to give you a short answer right away before we dig into details, is that this type of formulation gives more flexibility. For instance, if in some problems you may encounter discontinuity. For instance, you consider it a problem about a bar and its cross section is changing arbitrary, not arbitrary, but abruptly at some point, like it was one cross section and it suddenly became smaller, or material changed. Like in part of your domain, you have one material and there is some boundary after which some area after which there is different material. This is quite common case with composite materials. There are at least two components with completely different properties. And if you try to solve this kind of problem for this entire domain with partial differential equations directly, you will see immediately that you cannot do that because the solution would not satisfy the requirements for the continuity placed by the equation itself. So there are second derivatives for usually in partial differential equations in continuum mechanics in most cases, and so in order for those second derivatives to exist, to be not infinite, then this function which you are calculating derivatives of, it must be continuous enough. And it easily may be not continuous enough for some certain problems. It's very easy to bump into this kind of problem if you're talking about engineering problems. So this is one reason, and another reason is about boundary conditions. So this thing that I mentioned earlier, it's kind of very, very convenient also. So it gives you some flexibilities about the boundary conditions too. Okay, so we will start with that, about some very, very simple explanation about what is this weak formulation. I tried to explain why we need it. Let's try to have a look what it is on a extremely simple problem, the most simple that I could come up with as mass spring system. Like 1 degree of freedom, it's hard to imagine anything more simple in mechanics, right? So there is a mass supported by a spring in gravity field, and let's say we want to find the position of this mass. So it will go a little bit down. The spring is going to be stretched because of gravity, right? And you can easily solve this, of course, right? You can write the balance of forces. So the elasticity force in the spring, the linear force with respect to displacements, must compensate for the gravity force, and therefore you just write this solution. Super easy, and well, there are no explicitly differential equations here, but this is kind of analog for this system of this strong formulation. So to give you some first idea about what those variational formulations are about, you can think about the principle of minimum potential energy, right? So you can write this form, how to calculate potential energy of this system for any given position u of this mass, right? And this is again school stuff, so you must certainly know that. And then you try to find a displacement u that gives minimum value to this potential energy. And you calculate partial derivative. Well, in this case, you have only one variable, so it's the same as full derivative, but you calculate derivative to find extremum of this function, and you find this solution. Okay, so exactly, strictly speaking, there is no variational principle yet here because it's super easy. But it's like the best analogy in very simple systems that I could think of. And of course, you get the same solution. But the approaches are different. You notice that in first you write balance of forces directly and find your displacement from there. And in the second approach, you are minimizing some form. And this form, in this case, it's potential energy, but it could be something else. And sometimes it's not really possible to give a precise mechanical interpretation of this form. In this case, it is, but it's not necessarily the case. So the second approach is about writing some kind of form for this problem. And then by finding extremum of this form, you find the solution. So it's a fundamentally different approach. We don't use balance of forces here. Of course, it's supposed to give the same results if everything is correct, but it's different. Okay, so let's try to generalize it a little bit. So let's say we have this form P depending on function u, and let's say that in this case, like this bottom line, I'm not anymore thinking about this simple problem, but let's assume that displacement u is a function of some coordinates, as we usually have in continuum mechanics. Displacements are functions of coordinates, continuous functions. And let's say we have some form P. Well, in many cases, it will be potential energy. It's quite all right to stick with that, but it doesn't have to be necessarily. And the variational statement for a problem will look something like that. To find displacement field u, like this whole displacement u depending on x, it's a function. To find this function u such that it provides this form P with some special value. Well, I was talking about extremum previously because it's a little bit easier to visualize it in your head, but it doesn't really have to be extremum. Like even for functions, one variable function, you is trying to maximum, minimum, but you also might have this kind of thing, right? So in all these three cases, there is zero derivative at a certain point, right? So it's some special point. And this is what I mean here, saying but that it doesn't have to be necessarily extremum, because it can be also a saddle point, like in 3 dimensions. I probably won't try to draw that. It's a little bit more difficult, and online participants don't see it anyway, but I think you get the point. So you find a special point, or not pointer, but special function distribution of displacements that provides this this form, this variational form, with a certain property, ensures that it has this certain property, and the certain property is described using this variational symbolics. So for any text function delta u, this first variation of this form must be equal to 0. Okay, I will show that a bit more general. So starting from this idea with, I'm not going to go deep into variational calculus. We don't have time for that at all, but just to let you know a little bit about those things, because this is what finite element method is based on. I don't know, fortunately or unfortunately. So the general statement of a variational principle, how it is. So we have some function u, some unknown function. Function might be function of coordinates, or function on time, or depending on time, doesn't really matter. And we write a functional or variational form for this function. So something that provides a scalar value for any function that we put into it. Like so, usually it's similar to a function, but it's about a function of a function. So usually a function, you feed it with a value and it gives you another value. That's how single variable functions work. And this is a function of a function. So you feed this thing with a function, like I put sine x, for instance, in as an argument, and it gives me some value, I don't know, 2 or 2.5, whatever. And if I put different function like cosine, for instance, instead of sine, it gives me different value, like 0.2. Okay, so this is what is usually called variational form, because we use those things in variational formulations, but it's essentially a function of a function. So I called it psi here. notation psi. And I use square brackets to distinguish between normal functions that are functions of a value and these functionals, which are functions of functions, essentially. Right? So this is my square brackets indicate that. So this is normal function. It can be vector function, but it's still normal function. And this is a function. And then we define this thing called first variation. Like formally, it's defined like this limit. It's very similar to normal differential like you use in functions, but it's defined for those functionals. Okay, so we put the test function with some multiplier, and the difference while this multiplier approaches 0, this ratio, this limit is what we call first variation. Okay, then any variational principle can be expressed in essentially in this form. So we are looking for a function u that provides that this functional has 0 first variation for any test function. Like I use this symbol any, which you might know from different calculus courses. Okay, so this is how it looks like, and the very simple examples that you can to have a feeling about this is those principles of minimum energy, for instance. Okay. So how does it look like? So for instance, the problem that we discussed last time, so this two-dimensional heat conduction problem. We discussed how to formulate differential equations describing it. So how does it look like being expressed in terms of this weak formulation? So there is this variational form, this functional psi, which is a function of a function of a distribution of temperature, and it provides some scalar value for any distribution that I put in here. And this is how it looks like. And then variational principle looks, variational formulation looks like this. So we want to find the distribution of temperature in our domain such that for any test function delta t, this first variation of this functional will be equal to 0, plus we ensure that at this boundary we have prescribed temperature T subscript A. And if you calculate this variation from this thing using the definition on the previous slide, or you're just using analogy with differential calculus, because it's essentially the same mathematically, right? So you can use pretty much all the same tricks as with normal differentiation, but keeping in mind that you are now talking about functions and not variables as arguments. So there is a lot of analogy between differential calculus and variational calculus, but of course you need to have some practice with it. And this is not the topic of our lecture, but there are plenty of books that give examples and provide tools, theorems to do those things. Okay, so if I solve this mathematically, I calculate this variation and ensure that it's equal to 0 for arbitrary test function, then it means that the following things must be satisfied. So you see that this Q with upper bar is the heat flux that we have on the boundaries. And this is integral over entire domain of our boundary. So wherever we have prescribed heat flux, we put it here. And it comes out as this. Okay, plus we have this one additional boundary conditions that is not anyhow included in this variational form, and we must prescribe it separately. So you can see that there is a difference between two types of boundary conditions when we use this variational approach. So there are some boundary conditions which are, in a sense, included into the variational form, And there are other boundary conditions which are not, which we must prescribe on top of this variational statement. And those are called essential. The latter ones are called essential boundary conditions. Like we really need them to prescribe them. And these are called natural boundary conditions, which occur naturally. And if we don't do anything, that means that we imply that there is a zero heat flux here. And then it will enforce effectively zero heat flux boundary conditions on all the boundaries where we don't prescribe anything, where we don't specify those essential boundary conditions. Okay, yeah. So I put here these words, and then this is something that you need to keep in mind when you are solving problems with finite element methods. So what really happens when you apply something on the boundary, and especially if you don't. And this what is natural boundary condition depends on this variational form that you are using, and it depends, of course, on the mathematical statement that you are using. For instance, in heat conduction, let's start with simple thing that is here. In heat conduction problem, it's usually like with default at least statement that is commonly used, it's usually zero heat flux. So if you don't specify anything, that means that this boundary will be effectively insulated. There will be zero heat flux, so it's thermal insulation. In mechanics, the question that was last one in our quiz, it's zero force. So that means that there is zero force applied on this boundary if you don't specify anything, which imposes some restrictions on the stress tensor on this boundary. In some cases, it can be more complicated. For instance, in electromagnetic problems, you can use different type of formulations for the same problem. You can use magnetic vector potential or magnetic scalar potential to solve even purely magnetic problem, not even electromagnetic coupled electromagnetic, but purely magnetic problem, magnetostatics. You can use different formulations, and they will provide you with different natural boundary conditions. So you need to be careful of that if you go into domain with different physics, and you need to be aware of what kind of variational form is used and what will be natural boundary conditions. It's not only depends on physics, it depends also on your variables here. Because in those two examples, there are different variables here as argument of this variational form. Okay. So that's basically what I wanted to talk. Yes, it's okay. I will not say exactly like you put it. So I would say that it's called weak, because if you look at this, so this is our differential statement. Like this is strong formulation, and it's strong because you have second derivatives here. So the solution that you are looking for must be continuous enough for your second derivatives to exist. But this thing, it only has first derivatives if you pay attention here. I didn't explain how to get it, but just if you have a look at it, you see that it has only first derivatives. So you can, with this formulation and numerical methods, you can find a solution that does not, strictly speaking, satisfy this statement, because those might be infinite, those second derivatives. So there are relaxed requirements with respect to continuity of your function. And this is why it's called weak, I think so. Okay, so this was about this mathematical introduction. And now we are going to talk about the finite element method itself. Do you need any break to have a rest, or we can just dig into the main stuff right away? Okay, so everybody is silent, which I suppose means that you are ready. You are not too tired yet. So we will make then a short break, do a short break before starting our practical exercise with coding as previous time. Okay, let's talk about finite element method and try to justify answers to the quiz questions that we had. So first, I will start with discretization, and this is one of the responses that were shown as not correct, but it's not entirely incorrect. It's just not the essence of the method, but it is a part of it. So first idea is that we really do this discretization of the domain. We split it into a number of fragments, which are called elements, and they have shared boundaries, and they have common nodal points or nodes, okay, as it's shown here. And those elements might have different shape, of course. So in a two-dimensional perspective, you might want to discretize your object with triangle elements, with linear triangular, or this kind of non-linear triangular with quadratic faces. Or you want to maybe have quadrilateral elements with linear sides or with non-linear sides, like quadratic, for instance. And those are all elements that you might see. And if you go into other dimensions, then like starting from one-dimensional problems, it's just not that great variety. It only depends on nothing about geometry here because it's just one dimension, but we can still approximate our body with linear segments, our line. So let's say there is some three-dimensional line. We can approximate it with linear segments, right? Or we can approximate it with quadratic segments. Or we can use some higher order splines to approximate it, right? And depending on this order of approximation of the geometry, it's about geometry so far yet, but it's connected to approximation of the unknown function usually. We will talk about that later. So in terms of approximation, you see that the number of nodes must be related to it. So if we cannot use just two nodes to describe quadratic approximation, right? So that's why it's different. So about two dimensionals, we discussed. About three dimensionals, what is used typically are those five types. So I would say there are geometrically four types: tetrahedral, pyramid, prismatic, and hexahedral that are typically used. And I just put here two examples of hexahedral elements, linear and quadratic ones. Of course, these three can also be quadratic as well. Okay, this is what you are going to see in finite element software. So what does it have to do with our differential equation or with our variational forms? So first thing that you must be aware of is this transition between local and global coordinates. So let's say we have some kind of quadrilateral element in two dimensions with four nodes, linear element. And those four nodes have some coordinates in our global coordinate reference, coordinate frame, right? And we would like to make a transition to local coordinates so that which always take values from -1 to 1 from node to node. So this node, left bottom node, is -1, -1 in terms of eta and psi and eta, and this is 1, -1, and so on. Okay, and mathematically we can establish a transition correspondence between those two using this Jacobian matrix, right? Which consists of partial derivatives of one set of coordinates with respect to another set. I suppose nothing new here, but we need to be aware about that because we will be formulating everything in terms of internally in terms of local coordinates. But then in order to fulfill like overall equations, we will have to switch back to global coordinates, of course. Using those internal coordinates, let's assume that we are talking about this temperature program, heat propagation problem that we showed very recently in 2 dimensions. And let's assume that temperature within this element in local coordinates changes linearly. 2 coordinates, and this is how it looks like. And it takes values T1, T2, T3, and T4 at corresponding nodes. Like you can put coordinates of those nodes, local coordinates here, and make sure that it does. Looks a little bit long, but it's like the simplest we can get in 2 dimensions at all. In 3 dimensions, we are going to have even more terms, but I will not show that and to ask you to do that in this class. Okay, so this is linear interpolation of temperature within this element if we know its values at the nodes. Okay, so this is essentially what finite element method does. At some point, we assume that we know values at all nodes, and then we assume how our known function behaves within elements for given nodes, like here, for instance. And then using those functions, we solve the overall equations, and we finally find those nodal values that we are kind of assumed to be known here. Okay, I will get to that later. So in this interpolation, we see in front of nodal values of the temperature, we see those things which depend on local coordinates, which are called shape functions. You remember there was a question about shape functions, and I remember that most of you answered correctly. So this is how we assume, how we described our assumption about the behavior of the unknown function within finite elements. So this is used with shape functions. And the beautiful thing that we can use exactly this line for all elements in our discretization. The only specifics that it has here are those nodal values. So for different values, T1, T2, etc., we are going to have different value somewhere within the element, but we can use the same function always. Okay, so those shape functions are a characteristic of an element type. So they are not related to some particular element that we are considering, because after this transformation to local coordinates, all the elements look exactly the same. Okay, so then I have to get a little bit more boring, maybe. So then I write this interpolation in the term of the shorter using this summation notation, and finally using this matrix notation. So, so N1, N2, N3, and N4 are these shape functions. So I make a matrix or row matrix out of those functions in this case, and I make a column of nodal values of temperature at the nodes of my element. And then just a product of this row vector and this column vector gives me exactly this approximation. So this is the essence of the finite element method, how we approximate a known function within an element. And this essence is described using those shape functions. Okay, so we need all that to eventually solve this heat conduction problem using, as I mentioned, this variational form. And so what we have here, and we will apply this finite element discretization to this variational form, and we will assume that we can find the total value of this functional by summation of contributions for each element. So this is in most cases true, and in this particular case it is of course true. So inside this variational form, we have this sum of first order derivatives with respect to x and y, each of them to the power 2. So we are going to need to calculate this thing using our approximation. So we are going to need to calculate those derivatives. So this is our approximation. So this is basic assumption that the total thing, and this is energy, by the way, also. So this total energy, but it doesn't have to be in every variational principle, but in this case it is. The total energy is a sum of energies for each element. And within each element, we can use this approximation of temperature using shape functions, as we showed previously. And then we want to calculate derivatives. So let's start with derivatives with respect to local variables, because this interpolation, it depends on local variables. And then, well, basically this column is column of values. So there is nothing to differentiate here. Those are nodal values of temperature. We can only differentiate those shape functions. So we arrive at these two expressions with partial derivatives of shape functions with respect to one local coordinate and another local coordinate. And then if we use these two things and we combine them in a row vector, and we calculate a product of this row vector with the column vector composed of the same two things, that gives me exactly this sum of squares of first derivatives that is here. The only problem is that it's still with respect to local variables, whereas in the variational form, we of course have global derivatives with respect to global coordinates. Okay, but it's still essentially the same thing. So let's work a little bit on that. So then I put these descriptions here, like how we do that using nodal temperatures. And this column vector, for instance, let's start for it. It then looks like that. So there is again some column of nodal temperatures. This is all about one element, so temperatures at the nodes of this element. And there is some matrix, which is still a matrix of partial derivatives, composed of partial derivatives of the shape functions with respect to two local variables. So we have 4 shape functions and we have 2 variables, so it's a matrix 4 by 2. It's called B, it's called gradient matrix. So it's a matrix of derivatives of shape functions with respect to local coordinates. Okay. So I will use these notations B, and I will use this T superscript E to identify this as notation for this column of nodal values of the temperatures for a given element. So this E means for an element. So then this sum of squares of derivatives can be expressed like this, right? Because this row vector is actually the same column vector, but transpose of this vector. So we use transpose operator here, and this is what we get. Good. Then about this matrix of gradients. So if we know those shape functions, and we do know them if we have specified certain element, right? We assume some interpolation of a known function with an element. That means we have specified shape functions. And if we do know them, then we can calculate those derivatives. And in our case, this is our matrix of gradients, how it looks like, right? Okay. So let's get back to our variational form. So we talked about this thing. It looked like that. The only I still need to keep in mind that we were talking about local coordinates here, but in terms of integral, I will be able to make this transition quite easily using our determinant of our Jacobian matrix back to global coordinates. Okay, so for each element, this contribution to this total variational form can be expressed like that. And what's inside this thing? What I put in parentheses here in these brackets in a use notation key subscript E. is something that I would call for this problem element conductivity matrix. For problems about mechanical deformation, there will be element stiffness matrix in this place. So this is something that we can calculate, right? So this matrix B, we know it because it's derivatives of our shape functions. And this K is heat conductivity, property of the material. And if we know geometry of the element, we can calculate this integral over this whole element. And this is something that we can calculate. So it's a value for a given element, right? Okay, and this in this right part, there is this integral over the boundary. So now it transposes for a given element boundary of an element. And I again use here our interpolation for the temperature and nothing else. This product of matrix of shape functions and the column of nodal temperatures. Okay, I know that it's getting a little bit complicated, but we need to go through all these details. You will have these slides and you will be able to look at them more if you want to later. So let's talk a little bit more about those element conductivity matrices that I showed you, how we can construct it. So let's say we have an element with dimensions A and B, for instance. Then we can easily calculate this integral, and this is what. So I said that it's a value. It's matrix of value, not a scalar value. So it's not a function. That's what I meant, but it's a matrix, of course. So this product of two matrices will result in a matrix, and it will be a matrix 4 by 4 in our case of linear quadrilateral element. And this is how it looks like. We can explicitly calculate it for this kind of element. So it only depends on, the result only depends on material property, conductivity, and dimensions of the element. And in this particular case, only on the ratio of those sides, nothing else. And it's a symmetric matrix. Okay, and we are approaching the end of this mathematical journey into the finite element methods. So what we finally do, we calculate this sum over all elements to make this total rational form value out of those contributions for each element, and we compose all the nodal values into a single vector, global vector of nodal temperatures. So let's say there were T1, T2, T3, and T4 for the first element. This upper script 1 indicates that it relates to the first element. Then there's same things for the second element, and so on. There will be a little bit less elements than just number of 4 times number of elements because they share some nodes. Right? So it's not necessarily that you have 4 elements, 4 values for each element because they will be shared values. But anyways, we just compose this column of all values. It doesn't really matter how exactly we do that. Well, it does from technical implementation perspective, but from our ideological thing how to calculate, it doesn't matter in which order we place them. But we establish some kind of matrix that for a given element E allows us to extract values corresponding to that element from this global vector. So it's a matrix of zeros and ones. It's a matrix, there are only zeros and ones, and it's so that when we multiply it or we calculate product of this matrix with this global vector of temperature, it results in our local temperatures for this element. So it will be a little bit different for each element. Zeros will be in different positions. And how those matrices will look like depends on in which order we placed elements here in this global vector. But we can do that if we know that, of course, we know that's what we do. So in our case of let's say we are interested in a first element, and we put its displacements, it's not displacements, temperatures in the first positions in this global temperature vector. And so then we need just this matrix, which the number of rows is 4, because it's number of temperatures related to each element, and number of columns is equal to the number of total nodes. So dimension of this global temperature vector is number of nodes in our mesh. So we call it finite element mesh, this discretization. And this is this kind of matrix, and by calculating this product, we obtain this. Okay, for a different element, it will be a little bit different. So those ones will be in different positions, but that's quite simple, I suppose. Okay, so now that we have learned how to do that, so we have a tool to extract nodal temperatures from global temperature vector, and now we can calculate each contribution using local temperatures. Okay, and we find this sum over all elements, right? So this is how it looks like. This is our finite element discretization applied to this variational form, or to this function. So those are our unknown things here are global vector of nodal temperatures. So temperatures at all the nodes. We don't really know that before solving the problem, and we will be solving equations for them. And the rest things which is here in the brackets, we can calculate that. We know that this is our shape functions. This is those matrices identifying how we compose global vector, where we put displacements of temperatures for each element, and material properties and applied heat flux on the boundary. So we can calculate all that if we know how we did this discretization and we know the physical problem. And then we can try to find the set of those temperatures at nodes that satisfies our variational statement. So this variational statement is that for any test function delta t, this first variation of this variational form must be equal to 0. And we add what is essential boundary conditions, prescribed temperatures in case of heat propagation problems. So trying to satisfy that for any function results in this set of algebraic equations. And this is just exactly a set of linear algebraic equations. So there is a matrix K, which is global conductivity matrix, and right-hand side vector, column vector F. So by solving this linear system of equations, algebraic equations, we find those temperatures at nodes. And once we have, okay, this is already an example, and once we have found those temperatures, then we can get back into our approximation and recall that within each element, we know the distribution of temperature within each element if we know values of the temperature at its nodes. Okay, so in this case, we just assume that within an element, the temperature varies linearly. So once we have found those temperatures T from here at all nodes, then we just apply this again, this assumption. So within each element, it varies linearly, and we know the distribution everywhere of temperature. Yeah, I didn't get into this right now. We will get into that in our example, but well, to answer your question, yeah, basically when you are calculating these integrals, this is where you should do that. Yeah, this kind of integrals that when you're calculating, yeah, we will be doing that. Okay, so I understand that it's maybe a little bit messy because quite not so trivial stuff if you haven't dealt with it earlier. Maybe it's not very trivial, but as usually it's easier to grasp the idea when you're dealing with example. And this is exactly what we are going to do in the remaining part of our lecture. So, okay, so let me start explaining the example, then we maybe make a short break if you want to, and then we start try to code this thing and to solve this numerically. Exactly this heat propagation, heat conduction problem. Okay, so this we have our domain, prescribed temperature 0 at one side, insulation, which means 0 heat flux on another side, and prescribed heat flux values at 2 remaining sides. We will be using these simple elements, right? Rectangular elements for this example to make it simpler, and then we will compose nodal values of nodal vector of nodal temperature values of 4 elements, and we will compose vector of all nodal temperatures, and then we will try to solve this problem. Okay, I will. It will be very easy. This transition from local coordinates to global will be very easy here because we are considering rectangular elements, but it's essentially not that much different from any. Yeah, I will show you. I will give you an assignment also about the finite element method, and in instructions for assignment, I will show maybe a little bit in more general way how to deal with this transition, because you are going to need it for your assignment. Okay, so shall we make a break for how long? Do you want 7 minutes or less or more? Does anybody need a break overall, or I should just keep continuing? Because for me it doesn't matter. It's mostly for you. It's a bit difficult to receive a lot of information in a row. Online participants, do you need a break at this point?
Oh, I don't think so, but I don't know anybody else. For me, it's good to go if everybody else is willing to.
Okay, let me put it different. If anybody wants to have a break or feels that he would benefit from a break right now, please let me know now. Okay. Okay, so let's maybe make a 5-minute break then. Yeah, I also think it's good because yeah, it's easier to perceive information. Okay, so 5-minute breaks, and then we will continue.
Sounds good.